in an experiment.
We don't know yet.
Why is light so far?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This time, how skull bone marrow could help you age better.
And how a radioactive lead isotope could be used to age the solar system. I'm Lizzie Gibney.
And I'm Nick Petrichow. New research in Nature has shown that skull bone marrow may be playing a key role in keeping you healthy as you age. Now, bone marrow plays a key role in making blood cells through a process known as hematopoiesis, where stem cells are made, which then go on to become all the different kinds of immune cells and red blood cells that make up the blood. But bone marrow and its ability to make new blood deteriorates as we age due to things like loss of critical blood vessels or vasculature, accumulation of fat, and inflammation. The researchers behind the new work wondered if this deterioration happens in all bones, as much of what we know about bone marrow comes from studies of the long bones, the ones that make up the legs and arms, and the pelvis. But there's a lot of different kinds of bones in the body. And in fact, the team found that the skull seemed to be quite different, a finding that may have implications for helping humans to age better. To find out more, I reached out to one of the authors of the new paper, Bong Co, and started, well, by admitting something to him. I must confess, before I saw this paper, I had no idea that the skull even had bone marrow, but it makes perfect sense now I know that.
Right, and that's actually not common knowledge. I think we imagine bone marrow to be in our arms and legs, the pelvis, which is actually the primary resource for a bone marrow transplantation, right? And when I first started research in David Scannon's lab at Harvard, I also did not know that the skull had bone marrow.
But researchers like yourself do know, or at least you do know now, that the skull bone marrow exists, and a recent finding has shown that it's more directly connected to the brain than previously thought, as there are channels between it and the meninges, the membranes that wrap around the brain. And that allows blood cells and immune cells to come in from the skull bone marrow itself. So it seems like it's playing an important role in immunology, but in your study, you were looking at aging. So can you tell me what the key question was that you were trying to answer?
Right. So our question was, would all bone marrow compartments in different bones age the same way? And the reason why I focused on the skull, aside from my initial interest, was the initial finding that we saw a substantial increase of bone marrow in the adult mouse skull that actually continued throughout the adult lifespan of the animal. And in most cases, we would actually see the same or decreasing hematopoietic function in most bone marrow compartments. So this massive expansion of the skull bone marrow was a very interesting finding. And so with that, we tried to image the vasculature because that is our primary focus in this expanding skull bone marrow. We employed several methods of transplantation settings and also tried to figure out how this bone marrow was expanding in the skull during aging. And the most surprising thing was that with the expansion, until the end of the lifespan of the animal, the skull bone marrow kept its hematopoietic function, its healthy function, and it actually increased hematopoietic contribution to systemic immunity.
So the skull bone marrow is expanding both physically by maybe a fraction of a centimetre and by increasing the amount of vasculature. So does this imply that as we age, the skull bone marrow is taking on more of a role? And if so, what implications does that have for aging more generally?
So because there's increasing hematopoietic contribution, we think that this is, in a way, trying to compensate for the other failing bone marrow compartments. And this is particularly important because there's actually increasing inflammation in the brain with aging. And since I described these channels to you, the meninges is directly involved in counteracting this neuroinflammation that's occurring during aging. So by having this expanding skull bone marrow compartment that remains healthy and functional, we think that's playing a very critical role in trying to suppress or counteract the neuroinflammation that's happening during aging.
And so how is it that you think the skull bone marrow is, I guess, more resistant to aging, if I can put it that way?
This is actually something that we're still trying to figure out. We do see actually that on a hematopoietic stem cell level, that the stem cells in the skull bone marrow do not become inflammatory. So they're not contributing to the bone marrow inflammation that's occurring during aging. And we also know from single cell RNA sequencing that the endothelial cells, which are a very critical component of the bone marrow, that the endothelial cells in the skull bone marrow stay normal, whereas they become inflammatory, they secrete all kinds of detrimental factors in the aging femoral bone marrow, for example. So we know which molecules are moving in which direction, but we still have yet to figure out how all this is regulated.
And we talked a lot about the experiments that you did in this study, and the majority of them were mouse experiments, but there was some human data that backs up what you saw in the mice, right?
We were very careful about this, of course, because this phenomenon could be rodent-specific, right? So we want to make sure that we could observe this skull bone marrow expansion in humans as well. So we were very lucky to collaborate with a very large hospital in Korea, and they had CT scans of human subjects. With this data, we could see both in males and females that there is increasing diploic space with aging. And so the diploic space is actually the space which would contain the bone marrow, and we could see the increase. And I should point out that this is actually not the only observation, but other studies have reported this without really attaching meaning to what that means.
So what do you think are the general implications of this study?
So I think for a very long time, we thought that all bone marrow compartments in various bones are similar to each other. So our study is actually showing for the very first time that components of the skull bone marrow are very distinct from other bone marrow compartments. So it's really redefining how we think about bone marrow heterogeneity. And I think it also improves our understanding of vasculature. So each organ would have a different organization and functional properties of vasculature, but we should not continue thinking that the bone marrow is just one collective organ, but the compartments of each bone piece or bone part could have a specialization, if you will. In terms of aging and resiliency, this actually does expand our knowledge of how certain organs or compartments could be resilient against aging, and there's a lot to be learned from this. And I actually like to say, this is kind of a joke, but not really. But I like to say our study should encourage everybody to use a helmet, right? To wear a helmet, protect that skull, because you're going to need that bone marrow when you age, right?
That was Bong Ko from the Max Planck Institute for Molecular Biomedicine in Germany. For more on that study, check out the show notes for some links.
Coming up, researchers have taken a step closer to making an isotope of lead useful for dating the solar system. Right now, though, it's time for the research highlights with Dan Fox.
Is the Nature podcast sounding a little quieter than it used to? If it is, you might be interested in new research into a species of bat that shows a remarkable resistance to age-related hearing loss. Many bat species rely on echolocation to find their way around. This requires them to detect even the quietest of echoes, and that means they need to maintain their hearing to survive. To understand how bats' hearing changes over time, researchers estimated the ages of wild-caught big brown bats and measured their hearing sensitivity. They found that even relatively elderly bats, aged nearly 13 years old, retained youthful hearing, with analysis of a portion of the inner ear revealing no significant sign of age-related degradation. The persistence of good hearing in bats could result from protective mechanisms that preserve the cellular machinery needed for the sense. And understanding such mechanisms might aid in the development of treatments to slow age-related hearing loss in humans. Hear more about that research in Proceedings of the Royal Society B. Search engine algorithms are not the main force steering people to misinformation. It's the users themselves who may be to blame. Personalised algorithms which shape what users see when they browse the internet are often thought to expose people to unreliable information. To test this, researchers analysed users' Bing searches during 3 months in 2022 and 3 months in 2023. The team marked content in the search results and on the websites that users visited as reliable or unreliable, based on ratings from 2 independent sources. They found that unreliable web pages appeared in 1.4% and 0.9% of searches in 2022 and 2023 respectively, and rarely appeared in the top results. The majority of interactions with unreliable web pages resulted from users specifically searching for these sites, suggesting that people's own actions are a stronger factor in accessing unreliable online content than search algorithms. You can find that paper with your search engine of choice, or go straight to Science Advances.
Next up, we've got a story about how a long-lived lead isotope could help researchers pin down how long the solar system took to form. Now, when scientists want to work out the age of something, they often use techniques involving the decay of radioactive isotopes. These unstable isotopes emit radiation, ultimately decaying to stable ones. And the time it takes for half an amount of a radioactive isotope to decay is known as its half-life, one of the important factors needed when calculating the age of something. Carbon dating, for example, relies on the decay of radioactive element carbon-14. This technique works on organic matter and has a limit of about 60,000 years. But there are of course other instances where researchers want to date things that are much older. In situations like this, researchers turn to radioactive isotopes with much longer half-lives. One that researchers have been interested in using since the 1970s is lead-205, which has a half-life of 17 million years. It was thought that this isotope, that's made in the centre of some stars towards the end of their lives, could be used to date things that happened at the dawn of the solar system. This isotope has characteristics that could make it a reliable clock. But there's an issue. The specifics of how lead-205 is made in stars have been difficult to figure out, so it's not clear how much was around when the solar system started, which makes doing dating calculations difficult. But this week, a team has mimicked the radioactive decay seen in stars to get a better handle on how much lead-205 would have been around, taking it a step closer to being a useful dating isotope. To find out more, reporter Benjamin Thompson spoke to one of the authors of the paper, Guy Leckenby from TRIUMPH, Canada's National Particle Accelerator Centre. Guy laid out a peculiar behaviour of lead-205 inside stars.
So most radioactive decay occurs in one direction very strongly. Once something's decayed, it's done. You cannot reverse that. But lead-205 is, let's say, very close to being stable, but not quite. And so when you put it in a stellar plasma at very, very hot temperatures, then the element it's decaying to, which in this case is thallium-205, can actually also become unstable itself. So the direction of whether it's thallium that's decaying to lead faster or lead decaying to thallium faster, that very much depends on the temperature inside the star. We're talking about millions of degrees, potentially even billions of degrees. And so nothing like anything we could find on Earth.
And so we have this curious situation then in some late-stage stars where you get thallium-205 decaying into lead-205 and lead-205 decaying into thallium-205. What was the question you wanted to answer?
What we didn't really know is exactly how fast that process was. And the key quantity here is actually Not necessarily which one wins out. We know that at the highest temperatures, in the core of stars, that the thallium decay is much faster, and that's actually the main way we produce this lead-205. The really big question that we needed to answer here was, how long does the lead-205 take to decay once it was produced? Because that determines if the lead-205 can actually escape the core of the star where it was produced and then be ejected into the galaxy, where it can then find its way into our early solar system. And that was something that was very difficult to predict from theory.
So at lower temperatures, as the lead-205 tries to escape the star, it can decay back into thallium-205. What would constraining the speed this happens allow researchers to do?
That's really crucial for working out how much lead we expect to find in what we call the interstellar medium, the space between stars from which our sun was formed. So if we go back to our carbon dating analogy, where we need to know the number of atoms we started with and the number of atoms we ended with to work out the time, this measurement is really crucial for working out the number of atoms that we started with in the early solar system.
But you haven't got sort of a star handy, so you had to work this out in the lab. And to work out how quickly lead decays into thallium, you had to look at it indirectly by looking at the opposite side of the coin, by working out how quickly thallium decays into lead.
Yes, exactly. So, I mean, ideally we'd measure the lead to thallium decay, but for technical reasons, it's actually not possible. So instead, we need to measure the thallium decay. And interestingly, thallium actually is stable on Earth. It doesn't decay. So it only decays when you put it in conditions like is found in the core of stars. So we actually need to recreate those conditions. And in particular, that means stripping off all of the electrons from the thallium atom. This is very hard to keep the ions in this state because they want to capture electrons at any opportunity.
So you've recreated the conditions in a star. What did you observe?
Okay, so once we've prepared those thallium ions, we need to keep them there. And so they have the opportunity to decay into the lead ions. And at the end, it's actually pretty simple. We just count how many thallium ions decayed into lead. And this lets us work out how long thallium takes to decay.
And then you can work the equation backwards to work out how long it would take for lead to decay to thallium inside a star.
Yeah, so once we work out thallium to lead, we can calculate how long lead to thallium takes. The trick is we need to incorporate our understanding of how plasmas work and how the thallium and lead is acting in a plasma. And so we can use our understanding of physics to work out how long lead to thallium takes across a whole range of temperatures. That allows us to understand that process happening in stars and work out how long that lead will take to decay or how much of it survives as it's being ejected from the star.
So now you've constrained how likely it is an amount of lead will be kicked out into space from a star approaching the end of its life. And this escaped lead isotope has an extraordinarily long half-life. What does this knowledge allow you to do?
Yeah, so these stars at the end of their life, they're ejecting their matter almost continuously throughout the galaxy. There's so many stars in the galaxy that this process is happening continuously. And so this amount of lead-205 builds up until we reach this steady state where the input from these dying stars counteracts the fact that the lead-205 is decaying. And so that sets the amount of lead-205 we expect to find in the gas from which new stars is formed.
And what does your research then tell you about our solar system then?
So now that we sort of understand how lead-205 is produced, then we can really work out how long our solar system took to form way back 4.5 billion years ago. And that's really what's crucial for our dating, that we understand how much lead-205 we're starting with, because once our sun is formed, it's formed from gas that condenses and starts to collapse. And once that collapse process happens, no new lead-205 is going to be mixed in to our solar system. And so we can work out how much that lead-205 has decayed, and that will tell us how long that collapse process took. We're using our understanding of lead-205 as a sort of clock to time that collapse process.
And what does this work not do, Guy? What are some of the questions that remain to be asked or answered, I suppose?
Before we measured this, there was just so much uncertainty around how long it took for lead-205 decay that we couldn't really use it. Now that we've sort of unlocked that, we can start to work on the other problems. The main problem, I would say, is our models of the interior of a star still don't always agree on exactly how hot it is. So because the temperature determines exactly how much lead-205 escapes from the star, better models that agree on the temperature inside the core of these stars is, I would say, the main thing that needs to be improved.
And what do you think further constraining this relationship between thallium and lead and working out how much lead-205 is kicked out of a star will enable researchers to do in the future?
So if we can prove that lead-205 works as a clock in the early solar system, then there is all sorts of studies in understanding the early solar system where this can be applied. We're talking about how long it took for planets to form, how long the sort of material condenses in these newly formed planets. If we can get lead-205 working as a clock, then it will be extremely useful in those early solar system studies.
That was Guy Leckenby from Triumph in Canada. To read his paper, look out for links in the show notes.
Finally on the show, it's time for the briefing chat, where we discuss a couple of articles that have been highlighted in the Nature briefing. Lizzie, what have you been reading this week?
Well, it's what I've been writing, actually.
Oh, right, so cheating.
It is a story that I have been writing, and it comes from a Nature paper. It's a really interesting study, partly because of the results, but also partly because of how they've done it. So it comes out of Google, and what they've done is use data from around 40 million smartphones, Android smartphones, and they've used it to improve the GPS tracking ability that your phone has, and also to better understand the ionosphere, which is the portion of the upper atmosphere where you have solar radiation, very energetic, coming in and knocking electrons off and leaving this big roiling area of ionized gas.
Okay, so I can see why Google might be interested in improving GPS and making your phone work better. But where does the ionosphere come in? And are the two sort of related? Does one lead to the other?
Absolutely. So radio signals are what GPS relies on. And the ionosphere, when it has these big fluctuations, when there are much bigger or much lower densities of electrons in the ionosphere, that delays your signals. GPS is all about the timing of the signals arriving at your phone. That's how it does the calculation. So if there are some big fluctuations, big variations going on in the ionosphere that you don't know about, your GPS could be out by 5 meters if you didn't correct for this. And during big fluctuations, say if there's a geomagnetic storm, there's a lot of space weather, this could be tens of meters. If you think about it, on a day-to-day basis, maybe that's not a huge problem, but GPS is used for, pilots landing, for some use cases where being very, very precise is very important. And we just need to better understand the effects of geomagnetic storms. There's a lot of, satellites up in space. So better understanding the ionosphere could be useful generally in science as well.
So they've got these millions of phones and then they're trying to map the ionosphere. How exactly does it work?
So the phones pick up 2 different frequencies at once. And what happens is when you have electrons in the ionosphere, and they slow down low frequencies more than they slow down the high frequencies. So what ends up happening is you get the same signal coming from a GPS satellite, but you get a big time difference, I say big, nanosecond time difference between your signals of different frequency arriving. And from that, you can work backwards and figure out how many electrons it must have effectively passed through, what the density of electrons is.
And as we discussed, this helps with GPS, but did they reveal anything else about the ionosphere other than by better measuring it, they're able to improve the GPS?
Yeah, well, what was really cool about this was, so we do already try and map the ionosphere because you have to do these corrections already. But we do that using the ground stations for global navigation systems, and they don't have even coverage across the world. So what was really cool about this was phones are in many more places where those ground stations are. So a phone's data is not as high quality as a ground station would be, but they found clever ways to kind of use enough of it and find the average of that it reduced the noise. But crucially, it was just in a lot more places. So they were able to create this map of the world that covered regions that just weren't covered by the regular maps that exist. So a lot of, for instance, Africa, Southeast Asia, some areas of South America, where until now there's quite scarce coverage, they were able to provide these maps. And they showed quite nicely big bubbles in the plasma that had formed that they were able to see in really high detail that hadn't been seen in those areas in that kind of detail before.
So they're really able to get like quite a detailed picture of the ionosphere then. But the bit you mentioned there about using everyone's phones, it sounds super interesting, but I've got an Android phone myself. I don't remember necessarily saying to Google, hey, use my phone to measure the ionosphere. So how exactly did they do this?
So if you have location services turned on your phone, I am not an Android user, but I know on my phone there's a little arrow if I'm using location services. So from what I've gathered from Google, if you've done that effectively in the T&Cs, it's that your data is also potentially going to be used for a study like this. They are very hot on their privacy though. What they've done is use these big averages, and if your little nick data point was somewhere very isolated, that meant that by using it, potentially you could be identified. Then they've cut that from the study. They haven't used it. So they've only used data that comes from areas where there are enough users that it can be anonymized. So nobody should be identifiable as an individual data point in this study.
And as you said, you're writing a story about this. What has been the reaction of the researchers you've spoken to?
They've been really, really impressed. So there are a lot of people, this is one of those areas where there's so much going on that we don't even think about. You just use your phone, use your GPS. I'm trying to find, where I'm this office I'm trying to get to. And, in order to get that level of precision, we have these maps being created all over the world that map the ionosphere, that allow us to correct for these bubbles that are happening in space, or not in space, in the edge of the atmosphere. And people working on these maps are thrilled, really. They think this is a really cool use of the data. It's a great data set, especially that gives this coverage that didn't previously exist. The one thing that came up, aside from the privacy, which I think they were fairly satisfied that was covered, was, is this data going to be available? Is it just for Google, or is this going to be, there for anyone to study? And that is something which it seems like will be happening, but I haven't yet got all the details of exactly how they're going to make it public. And of course, is it going to be live real-time data, which is what you need if you're doing it to make GPS better in the moment? Or is it going to be afterwards, which is still useful for science? It might be that there's been a big geomagnetic storm and you want to know what happened, you want to better understand how the space weather interacts with the ionosphere, then it's going to be really useful for that. So in both cases, I think people will be happy. It's just, in my book, also a really cool idea, because previously we thought of improving GPS for your phones, so your phone is better at knowing where it is, where you are. This has turned it on its head. It said, actually, it's not just the end use. Data from your phone can improve the very maps in the first place.
And now that Google has done this, is it possible for other researchers to do it, or do you just need the resources of someone like Google to access millions of phones to make it possible?
I think that's it. If you have some other way of putting rough and ready sensors in millions of places around the world, then that also would work. But pretty much, let's face it, that's in our phones. But this isn't the first approach to kind of crowdsource the data that our phones are collecting in this way. They also reference in the paper that they're trying to do seismology using your phones, kind of see if you can get early earthquake detections from different kinds of sensors based on your phone. So there's a sense that this is quite, an untapped resource. So there may be more interesting studies in the future.
Well, it certainly seems like it. I guess we are all walking around with little computers in our pockets, so it makes sense to use them. But for my story this week, we're going for something that's used millions of devices to a study that is just on a single person. So I was reading a story in Nature this week about a researcher who decided to treat their own cancer with a virus.
Wow. So how did that come about, that they were in a situation where that seemed like the best course of action?
So this person, Beata Halashi, she discovered that in 2020, she had breast cancer, and she'd already had a mastectomy. So she'd had the breast removed, and she'd had 2 recurrences since the breast had been removed of the breast cancer. And frankly, she said she just couldn't face another bout of chemotherapy. But she was an expert on viruses, and she'd read about a certain type of treatment called oncolytic virotherapy. And this is a therapy where you basically introduce viruses into the tumour. And what that does is it gets your immune system to attack the viruses and thus attack the tumour, shrinking it and possibly making it easier to remove or treat in the future. And so, faced with this news again, she decided to just take it upon herself to do this. Now, she wasn't an expert in this particular kind of treatment, but she was well versed in isolating and using various viruses. So her and some colleagues, along with some of the top oncologists in Croatia, where she lives, sort of got together and worked out how to do this. The oncologists were there to basically make sure nothing went wrong, and if anything did go wrong, they would treat her immediately with conventional therapy. But yeah, she tried this on herself.
Wow. Okay, I have so many questions. She must have been, what a situation she must have been in, first of all, to take this course of action. Did she actually, push the syringe? Was she the one giving herself?
No, it was one of her colleagues doing it. I guess it would be quite tricky to do it on yourself, but she did isolate the viruses herself, and she is one of the authors on a publication that they've made from this. I mean, obviously it's a case study, it's a single person, so it's not like a conventional clinical trial or anything like that, and they do caution about that in the paper. But yeah, no, she basically did take it upon herself to do this and took it upon herself to make sure the results were published too.
And what were the results? Did it have a positive effect?
It did. So what happened was that over the course of about 2 months, she injected 2 viruses, one after the other. So she started with a measles virus, followed by a vesicular stomatitis virus. And both of these are quite mild viruses, and they've been used in other trials of this kind of treatment before. And so she injected them one after the other. And what happened was that over the course of the treatment, the tumour shrank substantially and became softer. And it also detached from the muscle and the skin, which made it easier to remove surgically, which is then what they did.
Wow, that's amazing. And you mentioned this is a one of a kind, this is an N of one, but what kind of ethical procedures did they have to go through to make this happen?
Well, to make this happen, they had to go through relatively few things because obviously she had her own consent. She wanted to do this, and she was able to work with oncologists and stuff to make sure it was done in a safe way. The ethical considerations came up when she was trying to publish this, and a lot of publishers did not want to publish this because it involved self-experimentation. And some of the ethical concerns with that is that by publishing this, it may encourage others to do such self-experimentation, and they may not necessarily have the resources or the expertise like Kalashi did to actually do this with a good effect. And also, it's N of 1. We don't know how effective this is more broadly. It worked for her that one time. That doesn't necessarily mean it would work for more people. And people who have cancer are generally more susceptible to taking unproven treatments. It is a situation in which maybe people will try different things which may not have the right efficacy. So there were certainly ethical concerns with it, but because she did it on herself, at least, she had all the consent and everything, and they did make it clear in the paper that this should not be a first line that you do. Some other researchers said as well, there's nothing actually particularly new in this. The only thing that's new is the fact that she did it herself. There are trials that are ongoing for using this kind of virus therapy to treat cancers and to treat cancers in earlier stages. There's not been one for this breast cancer specifically, but, there's nothing especially surprising about this. And the one thing that we don't know as well is what the effect was of her doing the measles virus followed by the other virus. That's not been done before, but because it's just her, we don't actually know how effective that is or whether just the measles would have done it or anything like that.
So she was in a very unique position in that she was able to set up her own trial effectively that just involved her, and she had all the expertise around her and was an expert herself. But obviously most people who have cancer are not in that situation, and we want them to be listening to their doctors and not trying things out on themselves.
No, exactly. And science does have a history of self-experimentation. It has always been ethically fraught and it's always been there. But I think it is important to look at the data more broadly and, people listened to their physicians, etc., who were across that data. This was just a very exceptional case. And for her as well, what it's done is it's sort of transformed her research. Because of this experience she's had, she's now switched her research. She's got some funding to investigate these kinds of virus therapies for cancer in domestic animals. So for her, at least, it's had quite a big effect.
Wow. What a way to wrap up her story. That's incredible. Thanks, Nick. And listeners, for more on those stories and for where you can sign up to get more like them straight to your inbox, check out the show notes for some links.
That's all for this week. As always, you can keep in touch with us on X. We're at Nature Podcast. Or you can send an email to podcast@nature.com. I'm Nick Petrichow.
And I'm Lizzie Gibney. Thanks for listening.